This is Ana Daulas with the first video of the module Electromagnetic Optics for the course ECE 513 Intro to Optics and Photonics. In this video, we will revise the electromagnetic theory for optics. We're gonna introduce the Maxwell equations for an arbitrary medium. We're going to talk about what is the polarization and magnetization fields and how they relate with the electric and magnetic field. And we're going to describe electromagnetic wave in a dielectric medium. So as we know, light is not only a wave or a Gaussian beam, but light is an electromagnetic field. And because it's an electromagnetic field, we can describe it as two fields, two vectoral fields. It can be defined with the electric field and the magnetic field, and both fields depend on the space and the time. The relationship between the electric and the magnetic field is given by the Maxwell equations, where we know that the curl of the magnetic field is going to be equal to the derivative of the electric density field with respect to the time. But if we are in a free space, or remember a lot of time that when we think about free space is a similarity about talking being in the vacuum. This is the same if we say going into the vacuum or being in the air. That could be the electric permittivity of the vacuum. So then it's going to be the derivative of the electric field with respect to time. Similarly, the curl of the electric field is going to be related with the negative of the partial derivative of the magnetic field with respect to time. And then we have here the constant of the magnetic permeability and the divergence of both of the electric and the magnetic field that needs to be equal to 0. So I'm not sure if how well you remember, but the curl operator is just like having the cross product. So remember that the cross product is gonna give us the vector as an outcome. This is one example of how to do it for Cartesian coordinates. But then the divergence is gonna be the dot product. So the result of the dot product is gonna be here a scalar value. So when we think about, so we know that both the electric and the magnetic field are related with each other with respect to the Maxwell equations. But we cannot forget that for every component of the electric and the magnetic field, they need to satisfy the wave equation that we studied in module number 2. So in electromagnetic optics, we're going to define the Poynting vector as a measurement for the power. So the Poynting vector is the cross product between the electric field and the magnetic field. And because it's the cross product, it's really important to remember that the Poynting vector is perpendicular to both of them. And this is something like I could potentially ask in a multi-choice question, those ones that we cannot practice the concept. So remember that we measure the energy with the Poynting vector, but the energy is conserved, right? So that means that the power flow scattering from the surface within an incremental volume needs to be equal to the time rate of the change of the energy stored inside of the volume. So you just need to make sure that at the end of the day, the balance of the energy coming inside and outside needs to be equal to 0. So we were introducing on the first slide the Maxwell equations for the vacuum. But what is going to happen when we have a medium, right? We have a medium that is not the vacuum, it's just a general medium. So these two equations, the divergence equation, they're gonna stay the same as if the medium is vacuum. That's not gonna change at all. But there's gonna be a change for the curve of the electric field and the magnetic field, because now we cannot express the electric density, the electric flux density. That's not gonna be able to define as be linearly proportional to the electric field. And it's gonna be the same. In general, the magnetic flux density is different to the magnetic field. So as hopefully all of you have already taken some intro to electromagnetics theory, but we know that light propagates within medium, right? We know that light moves from air to water and maybe to oil, and it keeps moving for different type of medium. So it's really important to notice that when we change from one medium to another, we need to satisfy our boundary conditions. So what is the boundary condition? The boundary conditions cannot tell us that every field, in this case the electric field, but every field can be composed with the tangential coordinates to the surface and the normal coordinates to the surface that we pretend to transfer, to pass through. So we know that the tangential coordinates for the electric field and the magnetic field, they need to be equal in the surface. So that's going to be one of our boundary conditions. And then you're going to ask me, okay, so Anna, what's going on with the normal ones? So for the normal ones, we don't have continuity with respect to the electric of the magnetic field. The field that is going to be continuity is going to be the electric flux density and the magnetic flux density. So the normal component of the electric flux density, this is the one that needs to be the same in the interface with the two media, and the same for the magnetic flux density. The normal components needs to be the same. So when we are moving from one media to another, we need to satisfy those boundary conditions. Otherwise, light is not gonna go through, and we know that light moves from one medium to another. Alright, so relationships around. So in general, we can consider that the electric flux density and the magnetic flux density has some relationship with the electric field. So it's gonna be the summation of two fields, where one is gonna be, for the case of the electric field, the electric density field is gonna be some proportionality with respect to the electric field plus a polarization density field. And that polarization density field is gonna depend on the electric properties of the medium. So we're gonna have something similar with the magnetic flux density. The magnetic flux density is gonna be equal to the summation of some constant multiplied with the magnetic field plus the magnetization density field, where the magnetization density field is gonna depend on the magnetic properties of the medium. And a priori, we need to know more about the medium and their electric and magnetic properties to understand what is the relationship between them. So let's assume that we are in a dielectric medium that creates a polarization density field that in response to apply electric medium, right? So when we say that the electric medium is linear, means that the polarization field is gonna be related linearly with the electric field. If the medium is homogeneous, that means that both the polarization and the electric fields are invariant with respect to its position. If the medium is said to be isotropic, that means that they are parallel, they follow the same direction, and the behavior is the same across all the directions, all the angles. When we say that the system is non-dispersive, means that the polarization field in a particular time is only going to be dependent of the electric field at that time as well. So if we are thinking about signal and systems, if that's our background from electrical engineering or computer engineering, that means that we're going to say that the system is it's casual, because it depends only for the particular time. And then we can also say that the system is spatially not dispersive if we have a relationship of point 1/1 between the polarization and the electric field. So if we are assuming that our medium is linear, remember it's P and E field, they are proportional, they are linearly proportional, it's non-dispersive, homogeneous, and isotropic, we can write the polarization as some proportionality here. So here we're going to have some proportionality where, remember that epsilon sub 0, this is going to be my electric permittivity. And then that chi, that's going to be my electric susceptibility. So that means that at the end, my electric flux density field is the summation of the component with the electric field with the polarization field. But the polarization field, we can also express it in terms of the electric field. So at the end, we can say that D is equal to the medium electric permittivity multiplied with the electric field. So this formula right here, it's the same in terms of mathematically. It's the same as the one in the vacuum, just saying that now the constant going with the electric field is the medium electric permittivity, which is going to be the product of the vacuum or free space electric permittivity, and then a constant that is 1 plus the electric susceptibility. Similarly, we can have the same derivation for our magnetic field if we are assuming that the system is linear, non-dispersive, homogeneous, isotropic. So in that case, the magnetization field is going to be linearly proportional and parallel to the magnetic field. So our magnetic flux density can be expressed as the medium magnetic permeability multiplied with the magnetic field. So just as to remember here, then chi sub m, this is gonna be our magnetic susceptibility, and then we know that mu sub 0, this is our magnetic permeability. Alright, so we know that we have a medium. In general, our medium can have electric and magnetic properties defined by their corresponding susceptibility. So that's gonna generate some polarization and magnetization field when we apply an electric and magnetic field to the medium. And we know what is gonna be the relationship, the Maxwell equation, because now in a general term, we can write the electric flux density and the magnetic flux density in terms of the electric and magnetic field. And because the system is homogeneous, then both the electric permittivity and the magnetic permittivity is not going to be changing with the time, because we say that the system is also non-dispersive. And as we were saying before, every component of the fields needs to satisfy the wave equation. Where now the difference with the wave equation is going to be here, this term. So we are not using anymore the speed of the light in the air or the free space. We are using the speed of the light in the medium that we are. And we know that the speed of the light on the medium, we can relate it with the speed of the light in the air. So remember, C, this is going to be a speed of light in free space, which remember free space is the same as a vacuum or air. So that one, which is a constant, right? We know that it's a constant, but if we write in general, we can estimate it. But not only that, we know that the velocities are gonna be related with the electric and the electric permittivity and the magnetic permittivity. So we can also express the refractive index in terms of the magnetic and electric properties of the medium. And no, so let's assume that in a lot of cases we're gonna assume that a medium has no magnetic properties. So here is that our magnetic permeability is the same from the vacuum, so we can cancel each other the magnetic permittivity. So the refractive index is gonna be the square root of the ratio between the electric permittivity. And again, if we are in the case where the system is linear, non-dispersus, homogeneous, and isotropic, the electric permittivity of the medium is the electric permittivity of the free space 1 plus the susceptibilities. At the end, the refractive index is going to be the square root of 1 plus chi. This is one simple case, but what is going to happen if the medium is homogeneous? So that means that now it changes with the time. So every single field is going to change with the time. So the electric field, the electric permittivity, the susceptibility, the polarization, the electric flux density, the magnetic flux density, everything is to be now time dependent. So remember, here being homogeneous means like, not time dependent, space dependent. So when we solve a Maxwell equation, we need to be more careful, but also we need to have this relationship. We need to be careful about this dependence when we are solving for the car. So we need to have these dependencies for every component of the terms to be able to solve them. See you in the next class.